that the Laplace transform is meant to deal with. We'll give you a ready-made formula for this. We'll also tell you how to remember that formula. And the moment I talk about the exponential form for sine and cosine, what strikes me is the Now let's try and derive the Laplace transform for some of the standard functions. You might wonder why exactly I'm trying to include this particular video, because all over the web, across the textbooks, you would have the Laplace transform of these functions. But what different we would like to achieve as far as this discussion goes is that we would like to give you a physical interpretation of the Laplace transform and then impress upon you once again that the Laplace transform is meant to deal with differential equations with initial conditions. So watch out for those discussions which give you a detailed physical interpretation of the Laplace transform of these two functions, and of course the incidental mathematical discussions also be quite interesting. Now let's try and look at the Laplace transform definition of these two functions and then try and manipulate so that your mathematical burden is actually brought down significantly. So two things you can in fact take home as far as this discussion is concerned. One is the physical interpretation of the Laplace transform of these two functions. Very, very interesting. In fact, we would map all that to the simple pendulum, which you are quite familiar with at the intermediate level itself. And the second thing is how we are going to compare the mathematical burden if you are hitting upon the mundane way of dealing with the Laplace transform of these two functions. So let's get started and see what exactly in store for us. Now let's get started in earnest, trying to find the Laplace transform of these two functions. If you go by the mundane method, what exactly it suggests? It says that Laplace transform of a function f of t is given by f of s. Generally, it is a convention to use the bigger alphabet for the frequency domain and the smaller alphabet for the time domain, and then it's going to be multiplied by e power minus st. We have discussed at length what is e power minus st, and then dt, because you are integrating with respect to time, and then 0 to infinity. And once again, let me tell you that 0, that is where every engineering process in real time incepts at time t is equal to 0 and goes up to infinity. Now coming to our case, if I replace f of t by sine at, what exactly happens? You get the following integral that you have to deal with. It's going to be f of t is nothing but sine at, and if you are replacing f of t by that function, and the next function obviously would be e power minus st and then dt, right? But integrating this takes a significant amount of labor, because you will have to go for integration by parts. This should be the first function, this should be the second function, and after doing quite a few iterations you would be able to arrive at it. So this method is simply rejected, right? Because it calls for significant amount of labor. But however, in the process of dealing with the periodic functions, you will have to deal with this integral. We'll give you a ready-made formula for this. We'll also tell you how to remember that formula. But for now, this is a significant effort to begin with. So let's think of some out-of-box idea. Now what we can do is, can we reduce these two functions to the exponential form? That is the question. Can I reduce these two functions to the exponential form so that my integration effort is significantly reduced? And the moment I talk about the exponential form for sine and cosine, what strikes me is the Euler formula, which clearly tells you that e power I theta is nothing but cos theta plus I sin theta. Very, very important formula throughout the transform theory, whether you are talking about the Laplace transform, Fourier transform, FFT, or even Fourier series. This is going to be very, very helpful for you, especially for FFT. The complex number is the one that helps you conceive the idea, right? So the Euler definition now can we make use of? Yes, indeed. What I would do is, instead of finding sine 80, if I use this formula, I would be able to find the expression for both sine and cosine simultaneously. That is the advantage. Of course, if you want, you can express the sine in terms of exponential terms, cos in terms of exponential term. How do you do it? It's very simple. If you write e power minus I theta, since cos is an even function, it's going to be cos theta. Since sine is an odd function, what happens? It's going to be minus I sine theta, right? So this is what exactly you're going to get. Now what you can do, if you add these two, the odd function gets eliminated and your cos theta becomes I theta plus e power minus I theta by 2. And if you subtract these two, the even function gets eliminated and the odd function gets doubled, and that is where you will have sine theta is nothing but e power I theta minus e power minus I theta by 2i. So 2i rather, not factorial, it's 2i. Can I rewrite that as 2i, where I is a complex number? So you can express using these two exponential either cos theta, these two exponential as sine theta. But we'll use directly this so that simultaneously I'll be able to get the Laplace transform for both of this. Let's see how to do that. So now what I would do is I would consider the following: 0 to infinity. I'm not going to use either sine or cosine. Instead, I'm going to use e power I at, because I'm replacing theta by 80, right? Theta by 80, that is my angle, and that is going to be multiplied by e power minus st dt. Correct? All that I did is I just replaced the f of t function by e power I at, because this has a definition both for cos and sine. That is the Euler formula. So how would I go about this? This is very, very easy. Now this is 0 to infinity, 0 to infinity. And now can I club these two exponential terms? Indeed, what I would do is I would keep minus outside and I would say st. And then what about this? This is going to be minus IAT, right? And then dt. Clear? So what I did, I just took st and at, combined it, and I took minus outside so that you get back to the status quo, because minus st, minus of minus plus, because this is plus term, this is minus term, so this is term. And the very reason I keep it minus, because I have one of the limits as infinity. You have to be deliberating at every nuance, because if I were to make it positive, then you would have got confused at the time of simplification, because now if I put t is equal to infinity, what happens? This function will obviously go to 0. So therefore ensure that you keep it e power minus, so that your simplification is done very, very clearly. So now let's take this important integral to the next slide. So I have arranged it in such a way it remains an e power minus term, so that my upper limit is easily satisfied. So let's simplify this further. So what happens now? 0 to infinity e power minus est minus iat and then dt. So this is going to be my integration. Integrating an exponential function is very, very easy. The same function comes back, st minus iat. The same function comes back, and you are going to divide the denominator by the coefficient of t, which is nothing but what is that? Minus s minus ia, right? So this is the coefficient of t, because if you take t outside, it is minus s minus ai. So that's what exactly I have written. And what are the limits? The limits are 0 to infinity. Now it is very clear that the upper limit goes to 0. That is because if you have e power minus infinity, that becomes 1 by e power infinity, and that becomes 1 by infinity, and that goes to 0. right? So this is very, very clear. When I replace t by infinity, this entire term goes to 0. So I'm not worried about the upper limit. Lower limit, when I put t is equal to 0, this becomes 1 because e power 0 or any term to the power 0 is 1. So therefore this goes to 1, and what we have here essentially is 0 because that is the upper limit minus, and this becomes 1 anyway. So therefore divided by minus of minus can be written as plus because there is a minus here. Upper limit minus lower limit, there is already a minus here, so you don't have to worry. You have got AI. So you can remember it as artificial intelligence. So you have 0 plus 1 by s minus AI. So therefore this can be taken further. Now we have got the Laplace transform. So what is my FFS? FFS is got, and that turns out to be 1 by s minus AI, right? So this is what I have got. Now I got to simplify this because this is in the complex form. I have to rationalize it because I cannot have any complex number in the denominator. Why exactly I am doing that? Because I am seeking the Laplace transform of e power I a t. Remember, this is what I have achieved, right? Can I rewrite this as Laplace transform of, how I can rewrite this? I can rewrite this as cos at plus I sin at. Am I right? Cos at I sin at. Now if you apply the rule of linearity, because it's a linear operator, each term can be operated separately. So that means, can I say this as cos at plus I being a constant, I have taken out, and I can use the linear operator, that is L, to operate both the terms. So I have got this. See, now I have got a Laplace transform of a real number plus the real part and the imaginary part, because I comes over here, right? I should have an equivalent on the LHS also to compare. So obviously that I need to rationalize because I need to compare with the real part and the imaginary part. How did I do it? I used the principle of linearity because it's a linear operator. So each term can be operated independently, right? So now if I simplify this, if I rationalize this, I would be multiplying this by its conjugate. So what happens? You get s plus ai, and here also you are going to multiply by s plus ai, so that you have mathematical status quo. But when you multiply a complex number by its conjugate, what happens? You get a real number, right? That is the beauty of complex numbers. When you multiply by its conjugate, you get a real number, and you are familiar with this when we were dealing with differential equations and especially roots of the auxiliary equation. So this is very, very easy. And now I have got two terms. If I divide the denominator is a real number now. If I divide the numerator by the denominator, I'll get two terms, obviously. S by this plus one more term, the imaginary term, is a by s square plus a square. Now isn't this obvious that I'm talking about the Laplace transform of cos to be this and the Laplace transform of sine to be this? Absolutely easy and clear. No labor was spent in integrating, right? It was a very, very easy integration. What we did, we in fact started with the idea of integration by parts, which we rejected because the unnecessary labor it would demand. And as a consequence, what we did, we remembered the Euler definition, and which is very, very important, and we implemented it here. We sought the Laplace transform of this particular term, and then we kept it as minus because we have the upper limit as infinity. Remember, a very, very important one, because your integral will go to 0 when you substitute the upper limit. And the lower limit is minus because upper limit minus lower limit, this becomes minus of minus plus s by s minus ai. Because lower limit, when you substitute t is equal to 0, this entire thing becomes 1. That is where you have got 1 here. And remember, whenever you integrate an exponential function, you get the same exponential function, but you will have to divide that by coefficient of t. And if I take t out, what is the coefficient? Minus, inside the bracket, s minus ai. That's what exactly I have divided by. So this is all quite simple. And once I got my frequency domain function, that is s minus ai, I rewrote the definition of e power iat. I got this definition, and then I split this into two parts, real and imaginary. And of course, because the Laplace transform is a linear operator, so therefore I can operate each term, okay, inside this expression separately. And I rationalize this because I have an imaginary term here, so I also need to have an imaginary term in the numerator to compare, and therefore I rationalize this. And you know, when you multiply a complex number by its conjugate, it turns out to be a real number. And then when I divided the numerator, s by the denominator and a by the denominator, of course I comes, and when I compared, so I got the Laplace transform of cos at first and Laplace transform of sin at. And here one basic academic instruction for you, because most of the students whenever they consider the Laplace transform of sine and cos, they actually miss out cos. So s, it ends with s, so therefore s comes on the numerator. For sine, it ends with n, so it does not come in the numerator, but this a will appear in the numerator. Now this is something that is very academic and mundane. Now let's try and attach the interpretation of these two expressions, why exactly we get these two expressions, through a simple pendulum and also the differential equation of the simple pendulum and initial boundary conditions. That's going to be a very exciting discussion to follow. So now that we have established, now let us try and give physical significances to both these terms. Now let's get started with that discussion. Well, engineering and math are absolutely inseparable. We interventions day in and day out try our level best to make math as simple as possible and also of great practical value to every aspiring engineer. Do you want us to reach the masses? Please like us, share and subscribe. Do not forget to turn on the bell icon.